In this video, I would like to talk about model predictive control with numerical solution for spatiotemporal dynamic systems. Spatiotemporal dynamic systems are usually described by partial differential equations, and occur in many research fields such as physics, biology, chemistry, economics, and so on. The state variable of spatiotemporal dynamic systems is characterized by both the spatial variable x and temporal variable t. This partial derivative term is used for representing the diffusion phenomenon, and this term is used to represent the advection phenomenon. Then, many spatiotemporal dynamic systems can be described by equations that contain this kind of partial derivative terms. It is worth noting that, for example, Naive-Stork's equation, Schrödinger equation, wave equation, Euler-Bernoulli equation, and Maxwell equation are all belonging to a class of spatiotemporal dynamic systems. Therefore, the control of spatiotemporal dynamic systems is a challenging problem with a wide range of applications. Next, let me explain our motivation in this study. Generally speaking, control problems can be classified into three categories as shown here. This is the set of control problems. In this set, there is the set of problems that can be solved analytically. Also, there is the set of problems that can be solved numerically. The remaining category is the set of open problems. In my opinion, analytical solutions are more valuable and elegant than numerical solutions. However, the applicability of analytical solutions is limited to a narrow class of problems. As you know, the computational power of computer has been rapidly increasing. Accordingly, numerical solution methods using computer have attracted much attention in the control engineering field. You know, numerical solutions are practically important to overcome the problems that cannot be solved analytically. Recently, many computer-aided methods have been developed. For example, LMI, sum of squares, multi-parametric QP and so on. Following this kind of direction, in this study, we would like to provide a novel framework for numerically solving the control problem of spatiotemporal dynamic systems. For this purpose, we would like to adopt the model predictive control strategy in this study. Model predictive control is a form of control in which the current control action is obtained by solving a finite horizon open-loop optimal control problem, at each sampling time, using the current state of the system as the initial state. The optimization yields an optimal control sequence, and the first control in this sequence is applied to the system. Model predictive control is a kind of optimal feedback control, and its performance index has a moving initial time and a moving terminal time. Thus, control input optimization is repeated at each sampling time. There are several optimization methods that can be applied to solve the model predictive control problem. These methods are categorized into the offline optimization, and these methods are categorized into the online optimization. Actually, these methods are unsuitable for solving the optimization problem of high-dimensional systems. Spatiotemporal dynamic systems usually results in high-dimensional systems through a finite difference approximation. Hence, it is inappropriate to apply these methods to spatiotemporal dynamic systems. Also note that these papers have already shown that these continuation methods are much faster than these iteration methods in spite of getting enough high precision. Therefore, in this study, we would like to apply the continuation method to solve the receding horizon control problem of spatiotemporal dynamic systems. In fact, we have already proposed a framework of designing a model predictive controller for a class of one-dimensional parabolic partial differential equations without constraints. So, the objective in this study is to provide a framework of designing a model predictive controller for a generalized class of high-dimensional partial differential equations with constraints. The main contribution of this work is to extend the set of problems numerically solvable like this. This is the outline of this talk. Next, we would like to introduce some notation and the system model. Let these parameters be positive integers. Let x and t denote spatial vector and temporal variable, respectively. Omega denotes the spatial domain and round omega denotes boundary region. Z denotes the state vector and U denotes the control input. Several definitions about the differentiation are introduced as shown here. The notation prime denotes the transpose of a vector. These multiple integrals are denoted like these. And this is a kind of sine function. Here, we consider the spatiotemporal dynamic system written in a general setting as shown here. A is a vector-valued function that contain arbitrary partial derivative terms. Also, we consider boundary inputs like this. Moreover, we impose constraints on the system as shown here because model predictive control method is advantageous to deal with constraints. It is well known that inequality constraints can be reduced into equality constraints by introducing an auxiliary variable. Therefore, we just focus on the equality constraints in this study. The regularity and uniqueness of the solution for this system are beyond the scope of this study. We don't discuss about that. Next, we would like to consider the model predictive control problem. Now, we formulate the optimization problem. The control input at each time t is determined so as to minimize the performance index given in a general setting as shown here. T is the evaluation interval of the performance index. Phi is the terminal cost function. L is the cost function over the prediction horizon. The minimization of this performance index subject to the system equation can be reduced to the minimization of this performance index introduced using the costate lambda and the Lagrange multiplier mu associated with the equality constraints. Here, H denotes the Hamiltonian defined as this. Then, we first apply integration by parts to the computation of the variation in J here. Delta denotes the variation that means the infinitesimal change. Next, on the basis of the variational principle, we can obtain the necessary conditions for a stationary value of J bar. This condition must be satisfied for J bar to be minimized and it is called the stationary conditions or KKT conditions. Anyway, integrations by parts play an important role to derive the stationary conditions. This is a simple example of integration by parts that can be applied to the computation of the variation in J. From boundary conditions, we have this relation. Then, we can substitute this relation into this term. Applying similar calculations, we can analytically derive the exact stationary conditions for J bar to be minimized as shown in the next slide. So, the subsequent discussion is how to solve these conditions. Generally speaking, it is impossible to find analytical solutions of these conditions. Then, we need to develop a fast numerical algorithm for solving these conditions. It is important to note that these conditions can be divided into 4 parts. The equation enclosed red line is the time evolutionary equation of Z. The equation enclosed green line is the so-called terminal condition. The equation enclosed blue line is time evolutionary equation of lambda with its boundary conditions. And, the equations enclosed yellow line are called optimality conditions. In order to solve the obtained stationary conditions using a numerical method we must discretize these equations into finite difference equations. Therefore, we introduce these notations for denoting the discretized variable. X hat is the discretized spatial vector. Tau hat is the discretized temporal vector over the horizon. Let this z hat be denoted like this for notational simplicity. Let optimization parameters u hat k and mu hat k be combined into the vector defined like this. Using these notations, the discretized stationary conditions can be written in a general form as shown here. Each part of stationary conditions enclosed by each color line is corresponding to each discretized condition enclosed by each color line. Here note that the condition 6D and the condition 6E can be unified into the condition 7. This slide shows the procedure of a numerical solution method. For given the present state C hat and initial solution U hat, the state C hat over the horizon can be determined from the initial time t to the terminal time t plus t, that means form k equal 1 to k equal mt, using the condition enclosed by red line in the previous slide. After we obtain the terminal state, the terminal costate lambda hat mt can be determined using the terminal condition enclosed by green line in the previous slide. Next, the costate lambda hat over the horizon can be determined from k equal mt to k equal 1, using the condition enclosed by blue line in the previous slide. For given capital U hat and Z hat 1 at time t, the state C hat and the costate lambda hat over the horizon can be determined so as to satisfy the conditions enclosed by red, green, and blue line. However, the remained conditions enclosed by yellow line is not necessarily satisfied. That means this f is not necessarily equal to 0 for given capital U hat. If f norm is equal to 0 for given U hat, then we obtain the optimal solution that satisfies the stationary conditions. So, F-norm is used to evaluate the optimality performance. Several algorithms have been developed such that F-norm can be decreased by suitably updating capital U hat. Recall that online methods can be classified into iteration methods and continuation methods. The procedure for iteration method is summarized here. First, we compute z hat and lambda hat over the horizon using the conditions 6a, b, and c. Next, we update u hat as shown here so that F-norm can be decreased. Then, this process is repeated until F-norm becomes sufficiently small. Therein, alpha is step length parameter. If S is given by the gradient of Hamiltonian, the method is called the steepest descent method. If S is given by the Hessian of Hamiltonian, the method is called the Newton method. On the other hand, the procedure for continuation method is summarized here. Similarly to this, we compute z hat and lambda hat over the horizon. But, in this method, we update u hat only once as shown here, where u hat dot is given like this so that this equation is satisfied. Here, xi is a positive constant. Therefore, f equals 0 is stabilized as the prediction horizon is moving. In other words, the optimal solution curve u hat is traced by integrating this differential equation without using iterative calculation. It is quite clear that the continuation method is much faster than iterative method because this method doesn't require the iterative calculation of this. So, we adopt the continuation method in this work. Next, I would like to show an illustrative example. The control of thermal fluid systems is a challenging problem. Thermal fluid system is described by Boussinesq equations that consist of momentum, continuity, and energy equations as shown here. Here, we consider the temperature control problem of the airflow for two-dimensional square domain. V is the velocity, P is the pressure, and theta is the temperature. Here, we consider the gradient of the temperature in the boundary region as the control inputs. Here, we set the performance index as shown here. Theta sub f denotes the desired temperature. The parameters employed in numerical simulation are shown here. This slide shows the animation of the time response of the temperature under the control. If the control inputs are not employed, there is no change in the responsive state, because the initial state is set as a steady state. The target temperature is set as 310 Kelvin. The average computational time per one control cycle was 1.6 seconds. Simulation is performed on this personal computer. This slide shows the animation of the time response of the flow. Unfortunately, the real-time optimization was not achieved using this computer. If we could use a higher spec machine or apply a parallel computation method, then we might be able to achieve the real-time optimization. This slide shows the time response of the boundary control inputs. Finally, let me summarize my talk. We successfully established the model predictive control method for spatiotemporal dynamic systems. We analytically derived the stationary conditions based on the variational principle. We showed the contraction mapping method can be successfully applied to solving the obtained stationary conditions via numerical simulation. Finally, we would like to emphasize that the proposed method has great potential for a wide range of future applications that include the control of magneto-rheological fluid, turbulence flow, crystal growth concentration, and so on. That's it. Thank you for your attention.